Power factor optimization. Good morning, everyone. Today, we're diving into a critical, yet often misunderstood, aspect of data center design and operations: power factor optimization. We'll explore how maximizing power factor serves as the engine for efficiency, allowing us to improve performance, reduce costly waste, and ultimately maximize the capacity of our infrastructure. Defining the metric. To begin, let's clearly define power factor. Power factor, or PF, is essentially a measure of how effectively electrical power is being converted into useful work. Mathematically, it is the ratio of real power, the useful power measured in kilowatts, or kW, to apparent power, the total power supplied by the utility, measured in kVA. Our goal is to achieve a power factor of 1.0, also known as unity, which signifies perfect efficiency where all supplied power performs work. Efficiency, in this context, is about maximizing the usable kW for every kVA drawn from the grid. The cost of low power factor. When power factor dips below unity, we incur several significant costs. Firstly, it leads to operational inefficiency. The utility must draw more total current to deliver the same amount of useful power. This excess current is known as reactive power. It performs no useful work but generates unnecessary heat in cables, transformers, and switchgear. This heat represents pure waste. Finally, from a financial perspective, many utility companies impose significant surcharges or penalties if a facility's average power factor consistently drops below a threshold, typically 0.95. UPS input power factor. Our uninterruptible power supply, or UPS, is the first critical component we must analyze. The UPS acts as the primary load on the utility grid, and its input power factor is crucial. Historically, older UPS systems, specifically those using 6-pulse silicon-controlled rectifier or SCR designs, exhibited a poor input PF, sometimes as low as 0.75. This poor performance created considerable upstream issues, including high harmonic distortion and the necessity to dramatically oversize infrastructure like generators and feeder cables to compensate for the inefficiency. The rise of IGBT rectifiers. Fortunately, technology has evolved dramatically. Modern UPS systems now employ insulated gate bipolar transistor, or IGBT, front-end rectifier designs. This technology enables active power factor correction, active PFC, where high-speed switching circuits dynamically shape the input current waveform to perfectly match the voltage waveform. The result is a substantial improvement. Modern UPS input power factors often exceed 0.99 at full load, effectively eliminating utility penalties and dramatically reducing total harmonic distortion. UPS output power factor rating. Beyond the input, the UPS output rating is equally important for our usable data center capacity. As the chart illustrates, an older 100 kVA UPS with a 0.8 power factor rating could only deliver 80 kilowatts of usable power. In contrast, a modern unity-rated UPS, with a 1.0 output PF, can deliver the full 100 kilowatts of usable power from the same 100 kVA rating. This 20% increase in deliverable real power directly translates into higher server density and better utilization of your costly UPS hardware. IT load characteristics. This high UPS output PF is essential because the IT load itself is highly efficient. Modern servers, storage, and networking equipment are equipped with internal power factor corrected power supplies. These loads naturally present a very high power factor, typically ranging from 0.95 to 0.99, back to the UPS. The importance here is simple: if the load is demanding near unity power, the UPS must also be unity rated to avoid capacity mismatch and truly maximize the available real power for your IT equipment. Correction techniques. For context, power factor correction is generally accomplished using two methods. Passive PFC uses simple, static components like capacitors and inductors. While reliable, it's heavy, bulky, and its correction level is fixed, meaning it doesn't adapt well to dynamic loads. Active PFC, on the other hand, is the gold standard for modern data center equipment. It dynamically adjusts to load changes, providing the near unity PF we discussed and, crucially, keeping harmonic distortion extremely low, typically below 5%. Infrastructure benefits. The benefits of a high power factor cascade throughout the entire data center infrastructure. By reducing total current draw, we achieve reduced sizing across the board, allowing for smaller, less costly conductors, circuit breakers, and transformers. Secondly, lower reactive current means less heat loss in the electrical distribution system, which directly results in lower heat generation. This, in turn, lessens the burden on our cooling systems. Considering cooling can account for 40% of the total power consumed, power factor improvements offer a significant systemic efficiency gain. The economic imperative. To conclude, optimizing power factor is far more than a technical compliance exercise. It is a critical economic and efficiency imperative. By committing to near unity power factor at both the utility input via modern UPS rectifiers and the UPS output via unity rated systems, data center operators can fully maximize the ratio of usable power to total cost. This directly leads to lower operating expenses, reduced infrastructure costs, and ultimately, a significant improvement in your power usage effectiveness, or PUE. Questions. Thank you for your time and attention. I am now happy to take any questions you may have regarding power factor optimization in your data center environment.